This is Lab 6 Magnetic Molasses. So these are the slides I'm going to be presenting. I got the introduction plus the principles, experimental procedure plus observations, the code, and then interpreting the simulation, and the what if and errors. Okay, so the purpose of this lab is to collect data for a magnet falling through a conductive tube of aluminum foil and to model the interaction using glow script. The materials I used were my phone, bar magnet, aluminum foil, and a meter stick. And the results that we got for the average time that we had is 1.24 seconds. And the physics principles that I've used in the glow script model is Faraday's law of induction, the Biot-Savart law, Lorentz force, Ohm's law, and Newton's laws. So the procedure plus the observations. So basically, we have this long tube of aluminum foil, and we drop a magnet down, and we do this by we do this doing the north face facing downwards. And we calculate the fall time using a stopwatch on the phone, and we repeat this 5 times for an average time. So the constants that we got were the tube length and the foil width and the inner radius, as you can see, and the mass of the magnet. And I used the previous magnet moment, dipole moment from the previous lab, and that's the graph that I got by using the constants that we have. And yeah, just some pictures on the right. So at first, obviously, we did the experiment, and then I had the bright idea to make a giant one, and it felt really slow. So that was really fun. So for the code, these are just the parts that I edited personally, and basically this is the dipole moment for this is the function definition for the dipole moment, which returns the dipole moment. The bottom left shows like the constants that I had that I already showed. And so the top shows the calculation for the magnetic flux, and then the right this basically ends up showing the forces and calculating like how that works out, because F net will end up being equal to F grav plus F magnetic, and we'll see that this causes a this basically shows what's happening with the velocity of a magnet when it enters and leaves, as well as in between. So the situation, basically what happened is due to Lenz's law, we can say that what it shows on glow script is that the red is counterclockwise and the blue is clockwise. Um, just due to the opposing magnetic field changes. If we use the Rodman rule, it's pretty easy to see that. And then the dynamics, when the magnet is flipped, the current direction switches pretty much because the B field points the opposite direction, but I mean it's pretty much like the same. And how does the total time in the tube compare versus the real world, and real world versus the computational model? The model shows a longer time, and this is probably because it doesn't account for air resistance, friction, or other things. And the shape of the graph that we got um, back here, we can see that it's pretty much stagnant when it's in the tube, pretty much, but it's not when it leaves or enters. So we can see that the force is probably unbalanced. It is unbalanced at the end and the beginning. So what if it errors? I think some assumptions that probably cause the errors are air resistance. Um, sorry, the bar magnet acting as a dipole. So we would use like just like this one equation straight up, but I don't think that really accounts for what it actually is, obviously. And the only forces are gravity and magnetic. And the errors are timing. It's not correct. The inaccurate dipole moment, and we didn't drop the magnet down the center because it hit the walls a decent amount. And what if? So basically, what if the resistivity of the conductor is 0? That would pretty much causing induced current to be like pretty massive and cause the magnet to fall slower because it induces a bigger B field. And if there were holes, that would mean there's obviously a less current around the tube, so that would make the magnet fall faster. All right, thank you.